Okay, why don't we go ahead and get rolling. Good morning, or whatever time it is, wherever in the world you are. My name is George Lamb with Nextivity. I'm the VP of Customer Care, and we're here for this webinar to talk about the use of passive components on both the QUATRA and the GO system. Now, of course, I'm not going to do this by myself. I'm going to get a lot of help, like all the help from Akun, one of our fantastic solutions architects, who's going to walk us through a presentation and do some show and tell. What I think I'm going to do is just kind of hang here back in the background. I'll monitor the questions as they come in. I might interrupt you every once in a while if I get a great question, but I'll monitor them also so we can bring them back up for the question and answer as we get done a little bit later. So why don't you go ahead and take it away, and I'll just hang out here in the background.
Okay, all right. Thank you, George. A very good morning to everyone. Thank you for taking the time out to join this call. As for our international audience, a good afternoon or good evening to you. So let me share my screen. So let me introduce myself. My name is Un. I'm a solution architect, as George has mentioned. I'm based in San Diego, California, which is the HQ of Nextivity, the maker of Cel-Fi Systems. So in this webinar, we are going to discuss the use of passive component, in the GO and QUATRA system. We are going to take a look at the input side on how can we split the incoming signal before feeding into the GO and QUATRA system. And of course, we are going to take a look whether do we want to split or combine the output signal of the GO and QUATRA system based on various situations, and how do we actually achieve that using a passive component. Of course, we'll discuss briefly the use of passive component that can improve the performance of the overall system in certain scenarios, right? As I mentioned before, Nextivity is based in San Diego, but we do have regional office scattered across the world. So if you like to seek some advice or assistance regarding our product or have any questions about it, feel free to reach out to us. As you can see on your screen right now, we do have all the contact numbers and information over there. We do have offices in Colombia for the Latin American market, Singapore for the Asia Pacific and Oceania market, Sweden, UK for the Europe, Middle East market, and of course, we do have a San Diego office for the North American market. So with this, let's go down into the main topic. What is a passive component? Passive component is any module that does not require power or electricity to operate. Examples of passive component are splitters, combiners, attenuators, load, duplexers, couplers. So all these are considered passive devices. One question for you will be, how about coax cable and antenna? Are those considered passive devices? Think about it. The answer is yes. Coax cable and antenna are still considered to be passive devices. Because why? They do not require power to operate. Okay? So we talk about what is passive devices. We know the definition of passive devices. The opposite of passive devices is active devices. Active devices is any module that require electricity or power to operate. Examples are your power amplifiers or optical converters. So now we know the definition of a passive and active. We are very clear about it. So why do we use passive devices? What are the advantages of it? As we mentioned previously, one of the main advantages of passive devices is it does not require power to operate. This means that passive devices can be installed far away from power point, or I do not have to run remote DC power to it. It's very convenient. Second example is, or I will not say an example, second advantage of passive devices is it's very simple. You have an input port and you have the output port, no complication. Third advantage is it is very cheap. Passive devices range from tens of dollars to hundreds, depending on the model and the make. The next advantages is very easy to install. As I said, there is no commissioning process for passive devices. You just need to connect your feeder line to the input, and the output just connect again to the feeder line, and then it will work as intended. Lastly is another major advantages of passive component. It is actually very long lasting and is very stable. So once passive devices are actually installed, they don't actually fail quite often. Their reliability is almost 99.99%. So as I said, once passive components are installed, they tend to last 5 years, 10 years. They don't require yearly maintenance, yearly checkup. So that is actually a very, very important advantages. So every advantage has a disadvantage. So for passive component, the main disadvantage is it is lossy. What does it mean? This means that any passive component will suffer a slight loss, right? Loss means that the output power is always less than the input power. But how much is the loss? We are going to take a look later on. But remember this, loss is also what we call insertion loss in passive component. Right. So after taking a look at the advantages and disadvantages of passive component, we are going to take a look at the common type of passive component that we use. The first one is actually a splitter. A splitter basically splits the input signal into multiple output ports equally. So on my hand right now, you can actually see a two-way splitter. So there are commonly used splitters are two-way, three-way, four-way, all the way up to around six-way, right? So you can see that this is actually a two-way splitter. You have incoming one port input signal, and then this power splitter will actually split it out into two equal ports over here, right? So this is also what we call a 3 dB power splitter. The signal at the output will be half of the input signal, right? So this is what we also call equal splitter. Now, think about it. What happens if I want the output port to be split unequally? So if that is the case, this is what we call a coupler. A coupler is also known as a uneven splitter, or some people actually call it a tapper. So again, we have a input over here, and then again we have two output ports. But this output port will be uneven. This will be split by a ratio. So for example, this is a 3 dB coupler. The output port difference is actually 3 dB. So for example, if we were to input a 10 dBm signal over here, the output port, the main output port here is actually 8.2 dB, and then the output port here will be 5.2. So the difference is actually 3 dB. So we can see that this is actually an uneven splitter. We have a single input, multiple output, same as an equal power splitter. Now, what happens if we want to have a multiple input and multiple output? This is where the hybrid coupler comes in. A hybrid coupler basically just split the incoming signal equally into multiple ports, right? So you can think of it as it combines and then split. So hybrid coupler, this is a 2x2. You can see that this is what we call a multiple input, a multiple output passive component. The next passive component we're going to take a look is actually a combiner. A combiner basically just combines multiple input into a single common output. Previously, I've shown you a two-way splitter. If I were to turn it around, you can see that I got two input ports over here and then a common output port. This becomes a two-way splitter, right? All passive components can be used either direction, whether is it on a single input port, and then it can become a dual input port for a two-way splitter combiner, right? So same case as a four-way splitter combiner, right? I can use it in one direction. It can also work in both reverse direction. So now we have seen the different type of a passive component. The next thing we're going to take a look is the important performance matrix of a passive component. What are the metrics to look out for when selecting a passive component? The first one is actually what we call insertion loss. As I mentioned previously, insertion loss is the loss of power when the signal travels across the passive component. So typical insertion loss for passive component can be ranged from 0.3 to 0.5. Typically, we want it to be as low as possible because you need to take care of the link budget for the whole system, right? But anything below 1 dB is considered good, but usually we are trying to target as low as possible. For example, around 0.3 to 0.5 for a two-way splitter. The next important matrix we look at is the VSWR, voltage standing wave ratio. VSWR actually just tells you how efficient the power travel across the passive devices, right? So in practical case, the power is not 100% transferred from the input to the output. There is always some power being reflected at the input port. So VSWR actually tells you that. VSWR is usually expressed in two different formats, either in a ratio format or in a dB format. In ratio format, we try to look as low as possible. 1.25:1, 1.2:1. In the dB format, it's the reverse. We try to look for as high as possible. 18 dB, 20 dB, 22 dB, 25 dB. Right? So these two values or these two formats are actually related. You can actually convert one to another. A good threshold for VSWR is 18 dB and above, 18, 20, 22. Whereas for ratio format will actually be around 1.25:1. So that's VSWR. The next performance metric is the maximum average power. This is the maximum power the passive component is designed to operate without damaging it. So it's very important. You need to know what is your max power coming into your input port and then select a higher power rating for the passive devices because you do not want to damage your passive devices when your input signal is working at full load. Common value is around, let's say, 10 watts, 50 watts, or 100 watts. The next performance matrix is frequency range. This is the range of frequency that your passive component is designed to work in. Example is 698 to 2700, 698 to 1955. So one thing to note is that please choose the frequency range correctly because if your frequency range is out of what the passive component is designed for, your performance is going to be significantly impacted. Lastly, we're going to take a look at the performance matrix called isolation. Isolation represents the ability of the passive device to reduce or prevent the signal from one port coupled to another port, right? So you can think of it as a signal coming in from one port leaking into the other port. We are trying to prevent or reduce this leakage over. So isolation plays an important part, especially nowadays. We are trying to prevent the signal from leaking from one port to another port to reduce the PIM issue. A good value for isolation, depending on the type, for let's say a splitter type, we are looking for isolation 18 to 20 dB and above, whereas for a coupler, we are trying to look for 28 dB and above. So these are the important performance matrix we look out for when we select passive component. So when,
hey Hawk,
yes.
You just mentioned an interesting word. You said the PIM issue. What does PIM stand for?
PIM stands for passive intermodulation.
So that's something we don't want, right? We don't want them leaking from one to the other.
Yes, definitely.
Okay.
Right. So let's continue. So we have taken a look at the several important performance metrics. The next section we're going to look at is where can we find these performance metrics. So on your screen right now, you can actually see two different data sheets for the same component. It's actually a two-way splitter, what you see over here. right? One is made by CommScope on the left, the other is actually made by Microlab on the right. So let's start with CommScope on the left data sheet. In the first line highlighted by the red circle, you actually see the frequency range, followed by the maximum average power, which is around 80 watts. And then you actually have the insertion, the isolation, followed by the last line, which is the VSWR. So you can see that you can find all these important metrics in the CommScope datasheet for the two-way splitter. On your right, we are going to take a look at the Microlab's two-way splitter again. It's in a slightly different format, but don't worry, all the important performance metrics are still there. So the first highlighted red circle tells you the frequency range, 694 to 2700 megahertz. And then at the very bottom, you can see that I highlighted 4 boxes. The first one is actually the output isolation, followed by the dissipation loss. We never talk about dissipation loss. In Microlab, they call it the dissipation loss. In actual fact, it is actually the same as what we discussed previously. It is also known as the isolation loss, the loss of power when you travel across a passive component. So these two are the same thing, except that Microlab like to call them dissipation loss. Then we can see the VSWR specs over there in the next box. And the last box is actually the power rating. You can see that the power rating for Microlab is 50 watts. It is less than the power rating for CommScope of 80 watts. So now we know how to find all these performance metrics in the data specification sheet or spec sheet. The next section we're going to look at is how do we use passive component in, let's say, a GO system. We're going to do that for a start, right? So if you were to take a look, now on figure 1 is a classic or the basic configuration of a GO system. You have a donor antenna connected to the GO system input port, and the output port of the GO is actually connected to an external antenna. Very classic, very basic configuration. We are going to use this and expand it out, take a one step further, right? So the question comes in, what happens if I want to split the output port of the GO system into 2 to support multiple external antenna, right? So if you take a look at figure 2, I can actually use a two-way splitter as we discussed previously. The output of my GO system can come into the input of the two-way splitter, and then the output of the two-way splitter, each port then can connect it to an external antenna, right? As shown in figure 2. Now, the question comes in, why do I want to do that? Let's say, for example, I have 2 rooms that I want to cover. They will be better served by a separate antenna in each room. That's a good example. Or second example is I have an L-shaped building or L-shaped space where one antenna can cover each straight line. That's another example, right? So we'll take a look at figure 2 is where we need to split the output port. We are going to take this concept one step further. Right now, we're going to take a look at the input port. So in figure 3, example is what happens if I have two different mobile wireless operators using the GO system. How do I actually support it, or how do I actually design it, right? So in figure 3, you can see that I have 2 GO systems, one GO system for each different mobile wireless operator. So for the input signal, instead of having 2 donor antennas, right, one for each GO system, I can actually just use one donor antenna and then split the incoming signal into 2. Again, by using a two-way splitter. The donor signal coming in and then splitting these 2 out, whereas each port can go to each different mobile operator GO system. But be careful, when you try to split the incoming signal, you need to make sure your link budget is able to support it. This means that there must be sufficient signal after the two-way splitter going into each GO system. right? So we have seen that in this example, in the input port, we are going to split the signal to support multiple GO systems. And then the output port, what happened in this case? For the output port, we need to combine the different mobile operator GO system into a common single point before connecting it to an external antenna. How do we do that? We can actually use a two-way combiner, right? So you can see that the two different signals from the two different GO systems coming into the two-way combiner, and then we have a common output port here to be connected to an external antenna, as shown in figure 3. So you can see that in figure 3, we split the input signal and then we combine the output signal. This is a very classic configuration, okay? Right? So now we are going to expand on figure 3, right? On the output port side. What happens if I want to support more than one external antenna? So in figure 3, we support one single external antenna. So what happens if I want to support two external antenna or even 3, right? So how do I do that? That will be figure 4. So in figure 4, instead of a two-way combiner, we are going to use a 2x2 coupler. A coupler comes in 2x2, 3x3, 4x4, 6x6. So in this example, we just discussed about the basic, but the principle can be expanded out to 3x3, 4x4. So over here at the output of each GO system coming into the two-port coupler over here, right? So once the input signal is connected to the coupler will actually combine and then split the signal into each output port 3 and 4. And then these two ports can be each connected to an external antenna as shown in figure 4, right? So you can see that on figure 4, we split the incoming signal. On the output side, we combine and then split the signal of the output port. So again, this is a fundamental discussion. You can actually apply this concept to expand it further, but like to strongly emphasize, always take care of your link budget, because every time you use a passive component, there is always a loss to it, right? A 2x2, a 3x3 will have more loss, 4x4 will actually have more loss. Same case as a two-way splitter, two-way, three-way, and then a four-way, right? So we see the concept of using passive devices in GO system. We can apply exactly the same concept, same scenario to a QUATRA 2000. So we are going to briefly take a look. So in figure 1 for QUATRA 2000 is a basic configuration, fundamental. I have a donor signal feeding into the NU, and the NU is connected to the CU by a Cat5 cable using the internal antenna. Classic fundamental configuration. Again, what happens if I want to use an external antenna on the CU? How do I do that? That will be figure number 2. So figure number 2, again, we are going to use a two-way combiner. The output port of the CU, which is EXA and EXB, these two signals will actually be coming into the two-way combiner, and then the common output port of the two-way combiner will go to your external antenna, as seen in figure 2. Same case on figure 3, we are going to split the signal on the input port to support multiple NU. Same case as in QUATRA 2000 is able to support multiple wireless operator, mobile wireless operator. So each NU can belong to one mobile operator. We can have operator A on one NU, operator B on another NU, right? So how do I do that? Again, I can make use of a two-way splitter. Donor signal coming from the donor antenna feeding into the two-way splitter, and then the output of each port of two-way splitter will go into each individual NU, right? So that is figure 3. So again, we want to expand it out on figure 4. What happens if I want to support multiple external antenna on my CU. So same case, at first, I will need to combine the output of my EXA and EXP port, on every CU coming into the two-way combiner, whereas the output port of the two-way combiner will go into a hybrid coupler, right? And then each output port of the hybrid coupler can be connected to an external antenna as shown in figure 4. So the concept of QUATRA 2000 is the same as a GO system, right? There's not much of a difference at all, if you can take a look. Right. So we have discussed on the use of passive component on the GO and QUATRA 2000 system. Of course, what we discussed is just a few ways and a few very simple fundamental example. But you can actually take this concept and then expand it out. But as I like to remind you again, always take care of your link budget, right? So we are coming up to the next section, which is the question and answer. If you got any question, you can type in the dialog box, or you can actually ask George about it.
So if you actually go back one page, I was just kind of having a chat. We were looking at figure 2 here, and we were trying to determine if the antenna in that situation would not be MIMO.
No, that antenna will actually not be MIMO. That actually is a SISO. But please remember, this is for QUATRA 2000 system. QUATRA 2000 does not support MIMO.
Okay, so if we did that on a QUATRA 1000, we wouldn't combine it into one, we'd keep it as 2 or run it into a MIMO antenna, right?
Yes, that's correct.
Okay. Okay, and there are some folks that might never have heard of QUATRA 2000. It's offered in limited marketplaces and actually combines multiple carriers together. Most of the world only has access to QUATRA 1000.
So if it's a QUATRA 1000, right, you don't actually need to combine it. You can just use another simple example is you can use a MIMO antenna that has 2 pigtails. They can connect directly to the 2 port, which is the EXA port and the MIMO port. There's another, another ways to do it.
Okay, could I split and have 2 MIMO antennas using 2 splitters?
Yes, you can, in actual fact. There is also another way, but it's not right, it's not wrong, but nowadays we try to reduce the number of antenna that is visible because customer perception is they do not want to see too many antennas, right? If we can combine the one antenna or the least amount of antenna visible, the less is the best nowadays.
Okay, but if we needed 2 for coverage, for instance, we could do that.
Yes, you can do that.
Okay. All right, I'm looking at the questions. I think we've covered most of what was out there. Hawk, you must have done a good job because there's not that many questions today.
Oh, thank you.
I did want to remind everybody while we're waiting for those last few questions to come through that we have another webinar planned for July 10th and 12th. That's going to be using the QUATRA Planner tool to be able to do a better job of planning your QUATRA installations. It's an online tool that helps you develop your BOM list. So again, that's on July 10th and 12th. Hawk, it looks like we may be done. There's no more questions. I think you did a pretty good job of covering the topic. So if nobody's got any other questions, what we might just do is wrap it up and tell everybody thank you very much for joining us today. And we will look forward to seeing you on future webinars.
All right. Thank you, everyone. Have a good day.